My name is Maria Mamelkina, and I'm from LUT University. And many years ago, I was graduated from the mining university as well. So today, I'm glad to participate in the online conference, and I would like to tell about treatment of mining waters by electrocoagulation. And a year ago, or over a year ago, I defended my doctoral thesis, and the thesis was mainly done under the supervision of Antti Hakkinen. And here are some results and findings. But first of all, I would like to start with mining waters, and let's just think what are the volumes. So to produce 1 ton of gold, we roughly need 250 million liters of water. And yes, you can see from the number that it is a big amount, but what is the equivalent? And for example, this amount equivalents to 50 days of water demand in St. Petersburg, or 10 years of water demand in Lappeenranta, where LUT University is. And just to calculate that, for example, last year, 3,300 tons of gold was produced. So yes, we need a lot of water, great volumes of water to produce metals. And of course, apart from the big amount of water that we use for mining, the water is also contaminated, and it is contaminated with cationic compounds, anionic compounds, suspended solids, organic compounds, toxic metals. But in this particular presentation, I would like to talk about sulfate and cyanide. And sulfate is toxic to the aquatic environment. It, of course, causes acid mine drainage and limits process operations. And cyanide is highly toxic for human being and also for the environment. And it also limits process operation and limits a lot safety as well. To get rid of these contaminants or to reach the limits suitable to reuse water or to meet the discharge requirements, water treatment techniques are developed, and they are classified as established and innovative. And established techniques again classified to active and passive, and innovative techniques are mainly classified as active techniques. And you can see the list of innovative active techniques, and the last one, electrochemical methods, and those are the methods I'm going to talk today in general, but about electrocoagulation in particular. So, what is electrocoagulation? I want you pay attention to the issue that the first patent for electrocoagulation was written over 115 years ago, and the first application in water treatment was in 1946, and the process behind electrocoagulation is that electric current is applied to destabilize contaminants in an aqueous solution. Anode and cathode materials are metals, and most commonly used ones are aluminium and iron. And aluminium and iron act as a destabilization agents. So aluminium and iron ions are released from anode. And the particle charge is neutralized by aluminum and iron ions, and thus the coagulation occurs. And you still remember that the first patent was written in over 100 years ago, and still the technique is innovative. And still the technique is under the development. So why? And I asked myself this question, and when I was studied this technique, I realized that the answer is mainly related to the mechanisms of removal, the mechanisms that are involved in these techniques. And you can see that for different contaminants, more than one mechanism of removal is involved. For example, for sulfate, it is enmeshment, charge neutralization, and co-precipitation. When for cyanide, depending on electrode material, those mechanisms are adsorption, enmeshment, charge neutralization, and complexation. So that is why I think one of the reasons it's not very easy to bring the technology for at industrial scale that easily and start applying it intensively. But still, we were aiming to scale up the technology, and we started from mesoscale with chemical coagulation experiments, where we studied the mechanisms, the coagulant dosing, and the removal efficiencies. Then we switched to microscale, and we here started the electrocoagulation experiments. We were studying mechanisms, process parameters, kinetics, equipment design. So you can see the tank cell and parallel plate cell. And also, of course, we were aiming to compare chemical coagulation and electrocoagulation performances. So then we switched to operation modes. We studied batch and continuous operation, equipment design, and scale-up parameters as well. And today, the present state of the research is at macro scale, and we still study the process performances for different contaminants, not only for sulfate and cyanide. We assess economically the technology. We try to characterize solids, and of course, we are aiming in dewatering and valorization of sludge. And the outcome finally is close, hopefully. Electrocoagulation water treatment plant for mining waters. And it is what I have done during my doctoral studies, and it is what we currently do. And of course, all the processes are influenced by different parameters. And when I just started, I found from literature that current density influences reactor design, electrode material, pH, presence of several contaminants, initial concentration of the contaminants. And I started to study those parameters. And while I was studying these parameters, I realized that there are real electrocoagulation process affecting parameters, and those are mainly conductivity, access to electricity, pumps that are related to flow rates, and of course the solid content in water. I would like you to have a quick look on these pictures. And can you guess or propose which picture has sulfate in water? You may answer, or you may just think for 5 seconds.
Maybe all of them.
Oh, yes. Thank you. All of them, and I hope that you all answer that all of them have sulfate, but of course the concentration of sulfate differs a lot, and you can see this bottom left-hand yellow picture, and the pH there, I don't know if you see my cursor. Do you see it? Okay, so here the pH is around 1, and the concentration of sulfate is 50,000 milligrams per liter. And coming back to electrocoagulation, here you can see the mechanisms of flux formation. And also the mechanisms of contaminants removal. And for sulfate, it is co-precipitation, decrease in solubility by charge neutralization, and enmeshment into a sweep flock. And from the graph, you can see the comparison of the performance of iron electrodes and aluminum electrodes. And here we compared the same current densities and the same amount of solids formed. And you can clearly see that iron electrodes have a better performance for sulfate removal. And cyanide removal. Coming to cyanide, we roughly use 100,000 tons to produce gold and silver, and 50 grams of cyanide is used in average per 1 ton of gold. And most probably some of you have a ring or an eye ring, and do you have any guess how much of cyanide we are wearing together with the ring or together with the eye ring? Rough estimation, is it like 100 grams or 1,000? Any ideas? Okay, I help you with that. So with the ring or with the eye ring, we are wearing roughly 200 grams of cyanide as well as gold. And yes, we keep on using cyanide, and there is definitely an acute need to treat cyanide-rich waters. So that is what we were trying to do again with electrocoagulation, and from the slide you can see the mechanisms of formation of flocks, and also the mechanisms of cyanide removal. So one of the mechanisms is complexation, and there are 3 other supporting mechanisms. Again, the decrease of solubility by charge neutralization, adsorption on flocks, and enmeshment into a sweep flock. And again, here the comparison of iron electrodes and the performance with iron electrodes and aluminum electrodes. And here you can see again that iron electrodes, they have better performance than aluminum electrodes, but still aluminum electrodes serve to some extent. And conclusions. So we talked about mechanisms. Yes, it's very difficult to define these mechanisms, and yes, there are always more than one mechanisms involved in electrocoagulation. And what we found that sulfate at the neutral to basic conditions is removed by enmeshment and particle charge neutralization, and in acidic conditions by particle charge neutralization and co-precipitation. Cyanide with iron electrodes is removed by complexation, particle charge neutralization, and enmeshment. And when with aluminium electrodes, there was no complexation, and only the adsorption, enmeshment, and particle charge neutralization took place. You remember that in both cases for sulfate and cyanide, iron electrodes were found to be more efficient to remove sulfate and cyanide by electrocoagulation. And for scale-up and design issues, it was proposed to use parallel plate cell configurations and to use electric charge as a scale-up, as the main scale-up parameter. And here are references. Of course, from the references, you find many more data and explanation on the mechanisms, and feel free to ask any questions now or contact me later to discuss the results and the research and the possible collaboration. So thank you.